For 100 years, we thought we knew exactly where Earth sits in the Milky Way. A quiet spot, halfway out, tucked safely in a minor arm of stars, safe from radiation, far from the chaos of the galactic core. Then James Webb turned its mirrors toward the dust clouds surrounding us, and everything we believed shattered. We are not where we thought. The spiral arm holding our solar system is not small. Our distance from the center is wrong. Even the shape of our orbit just changed. Right now, you are traveling through the galaxy at 450,000 miles per hour, and the destination is more dangerous than anyone predicted. If you enjoy discovering what science keeps hidden, subscribe now, because this journey goes deeper than you expect. Prepare yourself. Let's dive in. Astronomers spent a century mapping the Milky Way from the inside. Imagine trying to draw a map of a forest while standing in the middle of it, surrounded by trees blocking your view in every direction. That was their challenge. They could not step outside the galaxy to see its shape. They could not fly above the disk to measure distances. Every observation happened from Earth, embedded deep within billions of stars and vast clouds of dust. So they used light. They measured the brightness of distant stars and calculated how far away those stars must be. They tracked the motion of gas clouds swirling through spiral arms. They studied radio waves bouncing off hydrogen spread across the galaxy. Over decades, these measurements built a picture. Earth sits roughly 26,000 light years from the galactic center. Our solar system orbits within a small spiral arm called the Orion spur, a minor structure, a branch extending from the larger Perseus arm, safe, quiet, and predictable. This became the standard model. Textbooks printed it, planetariums displayed it. Every diagram of the Milky Way showed Earth in the same spot, and no one questioned it. Why would they? The measurements seemed solid. The math worked. The model explained what telescopes saw. But there was a problem no one wanted to admit. Dust. Thick clouds of cosmic dust stretch across the galactic plane, blocking visible light from stars beyond. These clouds hide entire regions of the galaxy from view. Early telescopes could not see through them. Astronomers filled the gaps with educated guesses, assuming the spiral arms continued in predictable patterns. They assumed distances stayed consistent. They assumed the structure stayed simple. Then infrared technology arrived. Infrared light passes through dust clouds like visible light cannot. Suddenly, hidden stars appeared. Structures behind the dust revealed themselves. The Spitzer Space Telescope started this revolution in the early 2000s, but its resolution had limits. It could see through dust, but not clearly enough to rewrite the entire map. That required something more powerful, something capable of detecting faint infrared signals from the farthest reaches of the galaxy, something precise enough to measure distances with accuracy never achieved before. James Webb launched in 2021 with exactly that capability. Its mirrors collect infrared light across wavelengths invisible to human eyes. Its instruments resolve details Spitzer could only hint at. When Webb turned toward the Milky Way's spiral arms, astronomers expected confirmation. They expected the new data to match the old models. Instead, Webb found discrepancies. Big ones. The Orion arm measured longer than predicted. Star clusters appeared at distances that did not fit. The edges of neighboring spiral arms sat in the wrong places. Something about our location was deeply, fundamentally wrong. And if our position was wrong, then everything built on that assumption collapsed. Our orbit, our exposure to radiation, our understanding of how spiral galaxies form, all of it needed revision. But the full scope of the error remained hidden, waiting in data yet to be analyzed. In March 2024, a team at the Harvard-Smithsonian Center for Astrophysics published findings that stunned the astronomy community. They had analyzed 3 years of James Webb data, focusing on star-forming regions across the Orion arm. Their conclusion broke decades of consensus. Earth sits approximately 3,000 light-years farther from the galactic center than every previous calculation suggested. 3,000 light-years. Not a small adjustment, not a rounding error. A massive shift that changes our entire galactic address. How did this happen? The old measurements relied on standard candles, stars with known brightness that act as cosmic yardsticks. Astronomers measured how dim these stars appeared from Earth, then calculated their distance. Simple physics, reliable math, except dust changed everything. Even small amounts of dust between Earth and a distant star make that star appear dimmer than it actually is. If you do not account for dust correctly, you calculate the star as farther away than reality. Multiply this error across thousands of measurements, and the entire map shifts. James Webb solved this by observing in multiple infrared wavelengths simultaneously. Different wavelengths interact with dust in different ways. By comparing how the same star appears across these wavelengths, Webb's instruments calculated exactly how much dust sat between Earth and that star. Then they corrected for it. The result revealed stars sitting closer than astronomers believed, which meant Earth sat farther out than the maps showed. But distance was not the only error. The team discovered our orbital velocity around the galactic center measured incorrectly as well. We are moving faster than predicted, about 20,000 miles per hour faster. This changes how long one complete orbit takes. It changes the forces acting on our solar system. It changes everything about our journey through space. The implications hit immediately. If Earth sits farther from the core, our exposure to certain types of radiation drops. The galactic center pumps out high-energy particles constantly. Distance provides protection, but farther out also means different gravitational influences, different encounters with passing stars, different risks from cosmic events we barely understand yet. Other research teams rushed to verify the findings. They pulled data from other James Webb observations. They reanalyzed old Spitzer measurements with new correction methods. They checked radio telescope surveys. Every independent verification confirmed it. The error was real. Our position in the galaxy had been wrong for over a century. Textbooks became outdated overnight. Planetarium shows needed updates. Every documentary about the Milky Way carried incorrect information. But more importantly, scientists realized they had been building theories on a flawed foundation. Models of galactic habitable zones assumed Earth's old position. Predictions about future stellar encounters used the wrong orbit. Calculations about our solar system's history depended on incorrect distances. The revelation opened a darker question. If we were wrong about something so fundamental, what else remains hidden in the data? What other assumptions need revision? Cosmic dust is not like dust on Earth. It does not settle. It does not blow away in wind. These particles, smaller than smoke, float in the vacuum of space for millions of years. They form from dying stars, from collisions between asteroids, from the remnants of exploded planets. Across the Milky Way, these particles gather into clouds, stretching thousands of light years. Some regions grow so thick with dust they block almost all visible light. For a century, this dust blinded astronomers. Optical telescopes see visible light, the same wavelengths human eyes detect. When visible light from a distant star hits a dust cloud, the particles scatter it. The light bounces in random directions. Most never reaches Earth. The star appears dimmer or disappears completely. Entire sections of the galaxy remained invisible, hidden behind curtains of floating debris. Infrared light behaves differently. These longer wavelengths pass through dust particles without scattering as much. Imagine trying to throw a basketball through a chain-link fence versus throwing a grain of sand through the same fence. The basketball, like visible light, bounces off. The grain of sand, like infrared, slips through the gaps. James Webb operates entirely in infrared wavelengths, designed specifically to penetrate the dust that blocks optical telescopes. Webb's primary mirror stretches 21 feet across, made of 18 hexagonal segments coated in gold. Gold reflects infrared light better than any other practical material. These mirrors collect faint infrared signals from objects billions of light years away or from dust-obscured regions right here in our own galaxy. The collected light funnels into 4 scientific instruments, each tuned to specific infrared wavelengths. One instrument, the near-infrared camera, captures images of star-forming regions hidden inside dust clouds. Another, the mid-infrared instrument, detects heat signatures from objects too cold or too obscured to emit visible light. Together, they reveal structures optical telescopes cannot see. Dense star clusters behind dust walls, newborn stars still wrapped in their birth clouds, the true shapes of spiral arms stretching across the galaxy. When Webb observes the same region in multiple infrared wavelengths, scientists compare the results. Dust affects different infrared wavelengths in predictable ways. By measuring these differences, they calculate how much dust lies between Webb and the target. Then they remove the dust's effect from the data, revealing the object's true brightness and distance. This process transformed our map of the Milky Way. Regions that appeared empty suddenly filled with stars. Spiral arms that seemed to end abruptly continued for thousands of light years. Star-forming zones that optical telescopes missed emerged in vivid detail. Each new observation added pieces to a puzzle astronomers could finally see clearly. But seeing through dust revealed more than star positions. It exposed our assumptions. It showed how much we had guessed, how much we had filled in with theory instead of observation. The galaxy we thought we knew existed mostly in models and predictions. The real galaxy, the one Webb sees, looks different, messier, more chaotic, more alive with activity we never detected before. And our position in this newly visible galaxy sits nowhere near where the old maps placed us. For decades, astronomers called it the Orion spur, a small branch, a minor offshoot from the Perseus arm, one of the Milky Way's major spiral structures. The name itself suggested insignificance. Spurs are features that do not matter much in the grand scheme of galactic architecture. They come and go. They fade between spiral arms. Our solar system happened to sit in one, and that seemed perfectly ordinary. The measurements supported this view. The Orion spur appeared to stretch about 10,000 light years from end to end, maybe less. Narrow, short, unremarkable. It contained our solar system, some nearby stars, a few star-forming regions like the Orion Nebula, and not much else of significance. Maps showed it as a thin line between the Perseus and Sagittarius arms, barely worth labeling. James Webb dismantled this understanding completely. When astronomers mapped the Orion structure using Webb's infrared data, the spur kept going and going and going. They traced star clusters farther than optical telescopes ever detected. They followed molecular clouds through regions previously invisible. They mapped the spiral arm's width at different points, finding it far more substantial than predicted. The new measurements shocked everyone. The Orion arm stretches at least 20,000 light-years across the galaxy, possibly more. Further observations continue to extend its boundaries. That makes it similar in size to the so-called major spiral arms. The width measures thousands of light-years thick in some sections, packed with young stars, dense gas clouds, and active star-forming regions. This is not a spur. This is a major galactic structure. The reclassification carries weight. Major spiral arms contribute significantly to a galaxy's dynamics. They influence how stars orbit. They create density waves that compress gas and trigger star formation. They shape the overall structure of the galactic disk. If the Orion arm qualifies as major, then the Milky Way's spiral pattern needs revision. Textbooks show our galaxy with 4 main arms. Webb's data suggests we might need to add a fifth, but size alone does not tell the full story. Webb also revealed the arm's composition. It contains far more massive stars than earlier surveys detected. These stars burn hot and bright, but they die young, exploding as supernovae within a few million years. Finding so many means star formation in the Orion arm happens more vigorously than anyone realized. Our neighborhood pulses with stellar birth and death on a scale previously invisible. This discovery reshapes our understanding of where we live. We are not floating in some quiet backwater of the galaxy. We occupy a major spiral arm, thick with stars, actively forming new solar systems, and possibly hosting dangers we never accounted for. Supernova explosions in nearby star-forming regions could send radiation waves toward Earth. Density waves passing through the arm could disturb the Oort cloud, sending comets toward the inner solar system. The implications grow heavier the more you consider them. Our solar system's history, the evolution of life on Earth, the future risks we face, all depend on the nature of our galactic environment. If that environment is more active and more dangerous than we thought, everything changes. And the revelations about the Orion arm were just the beginning of what Webb uncovered. Spiral arms are not solid objects. They are density waves, regions where stars and gas crowd together temporarily as they orbit the galactic center. Think of traffic on a highway bunching up at a certain spot, creating a jam that moves slower than the individual cars. Stars flow through these density waves over millions of years, spending time inside the arm before emerging on the other side. The wave itself persists, even as the stars come and go. Major spiral arms sustain themselves through gravitational interactions. They pull gas into dense regions where pressure builds. The pressure triggers star formation. The new stars light up the arm, making it visible across millions of light years. Minor spurs lack this self-sustaining mechanism. They form from temporary disturbances, then dissipate over time. They do not generate enough gravity to compress gas consistently. They do not form stars at the rate major arms do. James Webb found something unexpected in the Orion arm. The star formation rate rivals what happens in the Perseus and Sagittarius arms, the two structures astronomers definitely classify as major. Webb's instruments detected dozens of massive star-forming regions hidden in dust clouds. Each region contains hundreds or thousands of protostars, stars in the process of being born. These nurseries pump out new stellar systems at a pace that minor spurs simply cannot sustain. This suggests the Orion arm generates its own density wave. It pulls in gas from surrounding space. It compresses that gas into new stars. It maintains itself through the same gravitational mechanisms that govern major arms. If true, calling it a spur becomes inaccurate. It deserves recognition as a full spiral arm in its own right. But there is a complication. The Orion arm does not connect cleanly to the galactic center like the other major arms appear to. Major arms typically extend from the central bar, the elongated bulge of stars at the galaxy's core. They spiral outward from there, wrapping around the disk in grand, sweeping curves. The Orion arm seems to exist independently, floating between the Perseus and Sagittarius structures without an obvious anchor point. Some astronomers propose a new model. Perhaps the Orion arm is a bridge, a connecting structure that links two major arms together. Bridges form in many spiral galaxies, short segments that run perpendicular to the main arms, creating a web-like pattern across the disk. If the Orion arm functions as a bridge, that would explain why it appears substantial without connecting to the center. It would also mean our galaxy's spiral structure is more complex than the simple four-arm model suggests. Other researchers argue the arm might be ancient, a remnant from a past collision with a smaller galaxy. When galaxies merge, the interaction triggers massive bursts of star formation and can create new spiral features. The Orion arm's unusual position and vigorous star formation could be evidence of such an event, frozen in the galactic structure millions of years after the collision ended. Webb's data supports both theories and contradicts both. The observations confirm the arm's size and activity, but cannot yet determine its origin or how it connects to the larger galactic structure. More observations are needed. More analysis is required. The nature of our home spiral arm remains an open mystery, one that directly affects our understanding of galactic evolution and our own place in the cosmic architecture. What we do know for certain is that we live in a far more significant structure than anyone thought, and that significance brings consequences we are only beginning to understand. Right now, as you exist in this moment, you are racing through space at a velocity that defies human comprehension. Earth orbits the galactic center at approximately 500,000 miles per hour, not relative to anything nearby, not compared to the solar system's local motion. This is our absolute speed through the galaxy, the rate at which our entire solar system completes its orbit around the supermassive black hole anchoring the Milky Way's core. For comparison, Earth orbits our star at 67,000 miles per hour, fast enough to circle the planet in about 3.5 minutes if you could travel that speed at sea level. Our galactic orbital velocity is more than 7 times faster. At this speed, you could travel from Earth to the Moon in less than 30 seconds. You could cross the entire solar system from the inner edge to beyond Neptune in less than a week. Yet we feel none of this motion. No wind pushes against us. No force presses us into our seats. Everything in our local space, the planets, the asteroids, the comets in the Oort cloud, travels at the same velocity. We move together, locked in synchronized motion around the galactic center. Only by measuring the positions of distant stars over time can astronomers detect our movement at all. James Webb refined this measurement with unprecedented precision. Previous estimates put our orbital velocity at around 480,000 miles per hour. Webb's observations of star positions across the Orion arm, combined with advanced motion tracking algorithms, increased that number by roughly 20,000 miles per hour. That difference might seem minor compared to the total velocity, but it matters enormously for understanding our orbit's shape and duration. Orbital velocity depends on distance from the center and the mass contained within that radius. If we orbit faster than predicted, either we sit closer to the galactic center than thought, or more mass exists inside our orbit than models account for. Webb's distance measurements already ruled out being closer. That means extra mass hides somewhere between us and the core. Dark matter, most likely, the invisible substance that outweighs normal matter by a factor of 5 across the universe. This hidden mass influences everything. It shapes our orbit. It determines how strongly the galaxy's gravity pulls on us. It affects our interactions with nearby stars and spiral arms, and we cannot see it. We only know it exists because of its gravitational effects. Webb cannot detect dark matter directly, but by measuring velocities and distances with extreme accuracy, the telescope maps where dark matter must concentrate. The new velocity measurement also revealed something strange about our orbit stability. At this speed, in a galaxy with this much mass, our orbit should remain nearly circular. Gravitational forces should smooth out any irregularities over billions of years. Yet, subtle variations appear in the data. Our velocity fluctuates slightly over time, not enough to throw us into a wildly different orbit, but enough to suggest something perturbs our path regularly. Possible culprits include passing through spiral arm density waves, gravitational nudges from nearby star clusters, or even the influence of the galactic bar, the elongated structure of stars at the Milky Way's center that rotates at a different speed than the disk. Each time we encounter one of these features, our velocity shifts minutely. Over hundreds of millions of years, these tiny shifts accumulate. Webb continues tracking these variations, building a detailed history of our solar system's journey through the galaxy, where we have been, where we are going, and what forces shape our path through the cosmic dark. Earth has completed one orbit around the galactic center roughly 18 times since the planet formed 4.5 billion years ago. Think about that. 18 complete circuits through the entire Milky Way. Each orbit takes so long that continents drift across Earth's surface, species evolve and go extinct, and mountains rise and erode to dust while we make a single lap around the galaxy. Astronomers call this timespan a galactic year. For decades, the accepted length of one galactic year measured between 225 million and 250 million Earth years. This estimate came from dividing the circumference of our orbit by our presumed velocity. Simple geometry, reliable math, except both numbers were wrong. James Webb changed the calculation in two ways. First, the telescope confirmed we sit farther from the galactic center than previous measurements suggested. Greater distance means a longer orbital path. Second, Webb revealed we travel faster than astronomers believed. Higher velocity means we complete that longer path in less time than some models predicted, but the increased distance dominates the equation. The new calculation puts one galactic year at approximately 240 million Earth years, about 15 million years longer than the old median estimate. That might not sound dramatic, but over the age of the solar system, those extra millions of years per orbit add up. Where we thought Earth had completed about 20 galactic orbits, the real number sits closer to 18.5. We have traveled less of the galaxy than we believed. This matters for understanding Earth's history. Our solar system does not stay in the same environment as it orbits. We pass through different spiral arms. We encounter varying densities of interstellar gas. We move closer to star-forming regions, then farther away. Each environment exposes Earth to different levels of cosmic radiation, different risks from nearby supernovae, different chances of stellar encounters that could disturb the outer solar system. Scientists have long suspected connections between Earth's mass extinction events and our position in the galactic orbit. Some extinction events seem to cluster at regular intervals, roughly every 30 million years. If our orbit takes us through particularly dangerous regions on a predictable schedule, that could explain the pattern. Revising the length of the galactic year changes when we expect to encounter these danger zones again. The timeline of life on Earth maps against our orbital position. The Cambrian explosion, when complex life suddenly diversified about 540 million years ago, happened roughly 2 galactic years ago. The dinosaurs dominated Earth for almost an entire galactic year before their extinction. Humans evolved in the last tiny fraction of our current orbit, a cosmic eye blink in the galaxy's timescale. Understanding our true orbital period also affects predictions about the future. In about 240 million years, we will return to roughly the same position in the galaxy we occupy now. The spiral arms will have shifted. Star-forming regions will have moved. The dangers and opportunities our descendants face will depend on where the galactic environment takes them during that time. But Webb revealed something even more unsettling about our orbit. The path is not perfectly stable. Gravitational interactions with the galactic bar and density waves in spiral arms cause our orbit to change shape slowly over billions of years. Sometimes we drift farther from the center. Sometimes we edge closer. These variations happen so gradually that measuring them requires tracking our motion over decades with incredible precision. The data suggests we might currently be in a phase where our orbit is gradually expanding, moving outward, gaining distance from the galactic core. If true, future galactic years will take even longer than the current 240 million, and the farther out we drift, the more our environment changes in ways we cannot yet predict. The Perseus arm hangs in space about 6,500 light-years inward from our position, closer to the galactic center, brighter, denser, and far more active than the region we inhabit. Named after the constellation where it appears most prominent from Earth, this spiral arm dominates our inner galactic neighborhood. Everything about our environment connects to its proximity. Spiral arms are not stationary. They rotate around the galactic center, but at different speeds than the stars within them. Imagine standing on a sidewalk while cars drive past at varying speeds. Sometimes a car moves faster than you. Sometimes you overtake a slower vehicle. Stars experience the same relative motion as they orbit through spiral arms. We drift through the Orion arm right now, but millions of years ago we emerged from the Perseus arm, and millions of years from now we will enter the Sagittarius arm on the other side. James Webb mapped the Perseus arm with stunning clarity. The infrared observations revealed massive star-forming complexes that optical telescopes barely detected. One region alone, called the Perseus molecular cloud, contains enough gas to create over 100,000 stars like our own. The density of young, hot stars in this arm outpaces anything in our current neighborhood. These stars flood the surrounding space with ultraviolet radiation and stellar winds that shape the interstellar medium across thousands of light years. Our position relative to Perseus directly affects Earth's radiation environment. When our solar system occupied the Perseus arm millions of years ago, we lived much closer to these stellar powerhouses. The radiation levels were higher. The chances of a nearby supernova explosion increased. Some scientists theorize that increased cosmic ray bombardment during our time in Perseus might have influenced evolutionary patterns on Earth, possibly even triggering mutations that drove biological innovation. Now, we sit in the relatively quieter space between major arms. The Perseus arm's influence still reaches us, but attenuated by distance. Cosmic rays from its massive stars wash over the solar system continuously, but at lower intensities than when we traveled through the arm itself. This breathing room might be one reason complex life thrived on Earth over the past few 100 million years. Less radiation meant fewer mass extinction events caused by nearby stellar catastrophes. Webb also detected something unexpected about the Perseus arm's motion. The spiral density wave appears to be slowing down, not dramatically, but measurably. This changes the timeline for when we might encounter the arm again on our next orbit. Earlier models predicted we would enter Perseus in roughly 80 million years. The new data suggests that encounter might happen sooner, perhaps within 50 to 60 million years. When we do enter the Perseus arm again, conditions will change rapidly in cosmic terms. Stellar density increases, gas clouds thicken, radiation levels climb. The solar system will face different challenges, different risks, different opportunities for planet formation and destruction throughout the galactic neighborhood. Life on Earth will either adapt to higher radiation doses or suffer consequences we can only model theoretically. The Perseus arm also serves as a landmark for navigation through the galaxy. By measuring our distance from Perseus with precision, astronomers triangulate our exact position in the galactic disk. Webb's observations of star clusters in both the Orion and Perseus arms provided the reference points needed to correct our coordinate system. Without Perseus as a known point of comparison, the measurement errors might have persisted for decades more. Our relationship with this neighboring spiral arm shapes everything about our cosmic address: where we are, where we have been, where we are going, and what we will face when we arrive. Beyond our current position, farther from the galactic center, the Sagittarius arm stretches across thousands of light years. This spiral arm sits about 6,000 light years outward from the Orion structure. Like Perseus, on the inner edge, Sagittarius defines our outer boundary. Between these two major arms, we exist in what astronomers thought was empty space dotted with minor features. James Webb proved that assumption catastrophically wrong. The Sagittarius arm surprised everyone with its structure. Unlike Perseus, which appears as a relatively clean, well-defined spiral feature, Sagittarius fragments into multiple strands. Webb's infrared observations revealed at least 3 distinct subarms branching from the main structure. These subarms twist and curve through space, creating a complex web rather than a simple spiral. Some sections appear to connect back to the main arm, others drift away into the space between major features. This complexity challenges the classic model of spiral galaxies. Textbook diagrams show neat, evenly spaced arms wrapping smoothly around the galactic center, Real spiral structure looks messier. Arms split and merge. New features emerge from gravitational instabilities. Old features dissipate when their density waves weaken. The Sagittarius arm demonstrates this chaos clearly. What we call a single arm might actually be multiple structures layered on top of each other, all rotating at slightly different speeds. Webb identified one particularly strange feature in Sagittarius. A spur, a genuine minor spur this time, extends from the main arm toward our position. This spur reaches about 2,000 light-years into the space between Sagittarius and the Orion arm. It contains several young star clusters and active star-forming regions. Astronomers named it the Sagittarius spur, and its existence raises questions about how material flows between major spiral arms. Standard theory says gas stays mostly confined within spiral arms. The density waves compress it, trigger star formation, and hold it in place through gravitational forces. But the Sagittarius spur shows gas and stars stretching across the gap between major features. Something must be pulling this material out of the main arm. Perhaps gravitational interactions with the Orion arm create tidal forces that draw matter across the void. Perhaps the rotation of the galactic disk generates currents in the interstellar medium that channel gas along specific paths. Understanding these connections matters for mapping our true environment. If material flows between spiral arms, then we do not live in isolation. Our neighborhood receives fresh gas from Sagittarius. That gas might trigger new star formation near Earth over the next few million years. It might change the density of the local interstellar medium, affecting how cosmic rays propagate through our region. It might even deliver organic molecules synthesized in distant star-forming clouds, seeding the solar system with the building blocks of life. James Webb also measured the velocity of stars in the Sagittarius arm relative to our position. The data revealed something unexpected. Sagittarius rotates around the galactic center slightly faster than models predicted. This means the gap between the Orion and Sagittarius arms is slowly closing, not rapidly, but measurably over tens of millions of years. Eventually, our position might become part of the Sagittarius structure as the arms shift and merge. Or the opposite could happen. The Orion arm might drift outward, widening the gap. Spiral arms are not permanent structures. They form, persist for hundreds of millions of years, then dissolve as gravitational conditions change. The Milky Way 1 billion years from now will have a different spiral pattern than today. Understanding how arms evolve, split, and merge reveals how galaxies change over cosmic time. The Sagittarius arm serves as a preview of where we are headed. In roughly 60 to 80 million years, our solar system will cross the boundary and enter this outer spiral structure. Conditions there differ from what we experience now. Stellar density drops. Star formation activity decreases compared to inner arms like Perseus. The radiation environment shifts to different wavelengths and intensities. Earth's future depends partly on how this transition affects the solar system. At the heart of the Milky Way, a massive bar of stars stretches across the galactic core, not a spiral arm, not a disk, a bar, an elongated structure roughly 27,000 light-years long, packed with ancient stars that orbit differently than everything else in the galaxy. This bar rotates as a nearly rigid body, spinning around the central supermassive black hole like the hand of a cosmic clock. Its gravity dominates everything within tens of thousands of light-years. Most spiral galaxies contain bars. They form when gravitational instabilities in the galactic disk pull stars into elongated orbits. Once a bar establishes itself, it persists for billions of years, fundamentally changing how the galaxy evolves. Stars caught in the bar's gravitational field follow strange orbits, looping back and forth along the bar's length, rather than circling the center in neat paths. Gas flows toward the core along the bar, fueling star formation in the central regions. The bar also influences stars far beyond its physical boundaries. Its gravitational field extends outward, creating perturbations in the orbits of stars thousands of light-years away. Our solar system sits well outside the bar itself, but we feel its pull constantly. Every time we complete a fraction of our orbit around the galaxy, the bar's gravity tugs on us from a different angle. These repeated nudges add up over millions of years. James Webb observed the galactic bar in unprecedented detail. Previous observations struggled to see through the dust and star density near the galactic center. Webb's infrared vision cut through the obscuration, revealing the bar's true shape and orientation. The observations confirmed what radio telescopes suggested. The bar angles roughly 27 degrees from our line of sight to the galactic center. This orientation matters because it determines exactly how the bar's gravity affects our orbit. Computer simulations show that bars create resonances in galactic disks. These resonances are orbital radii, where a star's motion synchronizes with the bar's rotation in specific mathematical ratios. At these resonance points, gravitational effects amplify. Stars get pulled into different orbital shapes. Some resonances stabilize orbits. Others destabilize them, sending stars onto paths that cross spiral arms more frequently or drift toward the galactic edge. Our position appears to sit near one of these resonance points, not exactly at the resonance, but close enough to feel its influence. This proximity might explain some of the irregularities Webb detected in our orbital velocity. As we approach the resonance, the bar's gravity pulls slightly harder. As we move away, the pull weakens. The result is a subtle oscillation in our speed and distance from the galactic center over tens of millions of years. The bar also affects the spiral arms themselves. Its rotation creates density waves that propagate through the galactic disk. These waves compress gas into the patterns we recognize as spiral arms. Without the bar, the Milky Way's spiral structure would look completely different. It might not exist at all. The bar and the spiral arms form a coupled system, each influencing the other in complex ways that astronomers are still working to untangle. One consequence of this coupling concerns our future trajectory. As the bar rotates and the spiral arms shift, the resonance points move. What lies near a resonance today might drift away from it over the next 100 million years. This movement could gradually change our orbit's shape, either making it more circular or more elliptical depending on which direction the resonance migrates. Webb's measurements of the bar's rotation rate provided a critical piece of this puzzle. The bar spins slower than the disk rotates near our position. This speed difference means we periodically overtake the bar's gravitational influence, then fall behind it again. Each cycle takes roughly 150 million years. We are currently in a phase where the bar's influence is increasing. In 50 million years, we will reach maximum alignment with its gravitational field. Then we will begin pulling ahead again, entering a different phase of the cycle. Understanding the bar's influence reveals that our orbit is not determined solely by the mass of stars and dark matter within our orbital radius. The bar's gravity, the spiral arm's density waves, even the tidal forces from the Milky Way's satellite galaxies all contribute. Our path through the galaxy emerges from a symphony of gravitational forces, each playing a different note at different times, and we are only beginning to hear the full composition. 29,000 light years. That is the new distance measurement from Earth to the galactic center. Not 26,000, not 27,000. 29,000 light years, confirmed through multiple independent observations by James Webb and verified by cross-referencing with radio telescope data. 3,000 light years farther than nearly every astronomy textbook printed in the last 50 years states. 3,000 light years might seem like a rounding error on galactic scales, but distance governs everything about orbital mechanics and environmental exposure. Being farther out means weaker gravitational pull from the core. It means different exposure to radiation from the central regions. It means our orbit takes longer and follows a different path than calculations based on the old distance predicted. The revision came from improved measurements of RR Lyrae stars. pulsating variable stars that brighten and dim on predictable schedules. These stars serve as cosmic measuring sticks because their intrinsic brightness correlates with their pulsation period. By measuring how bright an RR Lyrae appears from Earth and knowing its true brightness, astronomers calculate its distance through basic physics, simple, reliable, and dependent entirely on accurate corrections for intervening dust. James Webb observed hundreds of RR Lyrae stars scattered between Earth and the galactic center. The infrared observations cut through dust that distorted previous measurements. Each star provided an independent distance estimate. When astronomers averaged these measurements, the result consistently placed us 3,000 light-years farther out than the standard value. The error bars were small. The result was definitive. Our galactic address needed updating. This extra distance provides some relief regarding radiation. The galactic center hosts a supermassive black hole with a mass equal to 4 million stars like our own. This black hole actively consumes gas and stars, generating intense X-rays and gamma rays that stream outward through the galaxy. At 26,000 light-years, Earth sits within a higher intensity radiation zone. At 29,000 light-years, the radiation dose drops measurably. Not enough to notice in a human lifetime, but over millions of years, the reduced exposure might have given life on Earth a slight advantage. The distance revision also affects our understanding of the galactic center's structure. If we sit farther out, then observations of the central regions cover a slightly larger physical area than astronomers thought. Features that appeared to be a certain size must actually be larger. The central star cluster, the disk of gas orbiting the black hole, the ring of star-forming regions surrounding the core, all need resizing in our models. Farther from the center also means farther from the central molecular zone, a massive reservoir of dense gas clouds that fuels star formation near the core. This gas emits radiation across the spectrum, from radio waves to X-rays. Its influence extends thousands of light-years, shaping the chemistry of the interstellar medium throughout the inner galaxy. Being 3,000 light-years farther reduces our exposure to this chemical influence. The solar system's environment is slightly more pristine, less affected by the violent processes occurring near the galactic heart. The new distance measurement also refined estimates of the Milky Way's total mass. Calculating galactic mass requires knowing both the orbital velocities of stars at different distances and their exact distances from the center. If distances were systematically underestimated, then mass calculations were systematically wrong. With corrected distances, astronomers recalculated the distribution of matter throughout the galaxy. The total mass barely changed, but the distribution shifted. More mass concentrates in the outer regions than old models suggested. Less mass dominates the inner galaxy. This redistribution has implications for dark matter mapping. Dark matter does not emit light, but its gravity shapes how visible matter moves. By measuring stellar velocities and distances accurately, astronomers infer where dark matter must concentrate. The new distance measurements revealed that dark matter halos extend farther from the galactic center than previous models predicted. We live deeper within the dark matter halo than we thought, surrounded by more invisible mass, feeling its gravitational influence more strongly. And that invisible mass might be doing more than just holding the galaxy together. It might be steering our path through space in ways we have not yet detected. Space is not empty. Between stars, between planets, between galaxies, radiation floods the cosmos in forms that would shred unprotected life within seconds. High-energy particles accelerated to near light speed, gamma rays from distant explosions, X-rays from matter spiraling into black holes, cosmic rays from supernova remnants. Earth's atmosphere and magnetic field shield us from most of this bombardment, but the intensity of incoming radiation depends critically on where we sit in the galaxy. The galactic center is a radiation furnace. The supermassive black hole at the Milky Way's core devours approximately 1 Earth mass of material every few years. As this matter spirals inward, Gravitational compression heats it to millions of degrees. The superheated gas radiates X-rays powerful enough to ionize atoms thousands of light-years away. Add to this the dense concentration of massive stars near the core, many of which explode as supernovae, and the central regions become nearly uninhabitable for life as we know it. Being 29,000 light-years from this chaos, instead of 26,000, provides crucial protection. Radiation intensity follows the inverse square law. Double your distance from a source, and the radiation dose drops to 1/4. Triple the distance, and it drops to 1/9. 3,000 light-years of extra separation reduces exposure by roughly 15% compared to the old distance estimate. That margin matters over evolutionary timescales. Consider cosmic rays, high-energy particles that zip through the galaxy at nearly the speed of light. Most cosmic rays originate from supernova explosions. The galactic center region experiences far more supernovae per century than our neighborhood. Each explosion sends shockwaves rippling through space, accelerating particles to devastating energies. These particles spread throughout the galaxy, but their density decreases with distance from the source regions. At our revised distance, Earth receives fewer cosmic rays from the galactic center than previous models calculated. The reduction is not dramatic, but over hundreds of millions of years, lower cosmic ray bombardment means fewer mutations in DNA, less radiation damage to atmospheric chemistry, and reduced chances of mass extinctions triggered by radiation spikes. Life evolved on a planet slightly more sheltered than we realized. The same applies to gamma-ray bursts, the brightest explosions in the universe. These occur when massive stars collapse into black holes or when neutron stars collide. A gamma-ray burst within a few thousand light-years of Earth could strip away the ozone layer, exposing the surface to lethal ultraviolet radiation from our star. The probability of such an event depends on stellar density. Farther from the galactic center means lower stellar density, which means fewer massive stars nearby, which means lower risk of close-range gamma-ray bursts. James Webb's distance measurement also revealed that we sit in a relative minimum of radiation intensity, not the absolute safest zone in the galaxy, but safer than the average position at our orbital radius. This happens because the Orion arm contains fewer massive stars than the Perseus or Sagittarius arms. Massive stars burn hot and bright, pumping out ultraviolet and X-ray radiation throughout their lives before dying in spectacular explosions. Living between major arms, in a region with lower massive star density, provides an environmental advantage for planets hosting life. However, this advantage is temporary. As our solar system orbits the galaxy, we move through different environments. In 60 million years, when we enter the Sagittarius arm, radiation levels will climb. In 140 million years, when we pass through the Perseus arm again, exposure will spike higher. These cyclical variations might correlate with biological events on Earth. Some researchers have proposed links between our position in the galactic orbit and mass extinction events. Though the evidence remains controversial, the new distance measurement allowed more accurate modeling of these future radiation environments. Scientists can now predict when Earth will face higher cosmic ray bombardment, when gamma-ray burst risks increase, and when the planet might enjoy radiation lulls similar to our current situation. This knowledge cannot prevent future disasters, but it helps us understand the broader context of Earth's history and future. What remains uncertain is how much protection distance actually provides. The galaxy is vast, and radiation travels far. Even at 29,000 light-years, we might not be far enough to escape every threat the galactic center poses. Astronomers borrowed the term from the fairy tale, the Goldilocks zone, not too hot, not too cold, just right for life. Originally applied to planetary orbits around stars, the concept scales up to entire galaxies. Some regions of the Milky Way are too dangerous for complex life to evolve. Others lack the heavy elements needed to build rocky planets. Somewhere between these extremes lies a habitable zone where conditions favor the emergence and survival of biological systems. The inner galaxy fails the habitability test for several reasons. Stellar density is too high. Stars pass close to each other frequently, and close encounters between stars can disrupt planetary systems, flinging planets into interstellar space or sending them spiraling into their parent stars. The radiation environment is too harsh. Supernovae explode more frequently in the densely packed core regions, bathing nearby worlds in lethal doses of cosmic rays. The gravitational environment is too chaotic. Tidal forces from the central black hole and the dense stellar population create instabilities that make long-term stable orbits difficult. The outer galaxy presents different problems. Star formation rates drop dramatically in the outermost regions. Fewer stars means fewer planetary systems, which reduces the total number of potential habitable worlds. Heavy element abundance decreases with distance from the galactic center. These elements, carbon, nitrogen, oxygen, iron, silicon, come from supernova explosions. They are essential for building planets and life as we understand it. Too far from active star-forming regions, and there might not be enough raw material to create Earth-like worlds. The galactic habitable zone lies between these extremes. Models suggest it extends from roughly 13,000 light-years to 33,000 light-years from the galactic center. Earth at 29,000 light-years sits comfortably within this range, not at the inner edge where radiation threats increase, not at the outer edge where planets might lack the chemistry needed for life, right in the middle, where conditions appear optimal. But James Webb complicated this simple picture. The telescope's observations revealed that the galactic habitable zone is not a smooth ring. It has structure. Some regions within the nominal habitable zone experience higher supernova rates due to active star formation. Other regions sit in voids where stellar density drops below average. The actual habitability varies dramatically depending on your precise location, not just your distance from the center. The Orion arm, our current home, appears to occupy a particularly favorable spot. Star formation occurs at a moderate rate, providing enough heavy elements without creating dangerous radiation environments. Stellar density remains low enough that close stellar encounters happen rarely. We sit between major spiral arms, avoiding the highest concentrations of massive stars that populate those structures. It is almost as if the solar system stumbled into one of the safest neighborhoods in the entire galaxy. Almost. Because Webb also detected threats we did not account for in earlier habitability models. Stellar streams, ribbons of stars torn from disrupted globular clusters or dwarf galaxies, pass through our region. These streams contain old stars moving at high velocities relative to the local stellar population. If one of these stars approaches the solar system, it could disturb the Oort cloud, sending comets toward the inner planets. The threat is real, measurable, and part of our environment. The updated distance measurement shifted our position slightly deeper into the habitable zone, farther from the dangerous inner regions. This adjustment improves Earth's long-term prospects for avoiding radiation catastrophes. It also raises intriguing questions about the distribution of life in the galaxy. If we occupy a particularly safe region, should we expect to find more technological civilizations at similar distances? Do habitable planets cluster at specific orbital radii where conditions optimize survival? James Webb cannot answer these questions directly, but the telescope is searching. Observations of exoplanets around nearby stars provide data on atmospheric composition, surface temperatures, and orbital stability. Each discovery refines our understanding of what makes a planet habitable. Each measurement helps map the true extent of the galactic habitable zone. What we know for certain is that Earth exists in a rare environment, not impossible, not unique necessarily, but rare enough that most places in the galaxy do not offer the same combination of safety and resources. Our position in the Milky Way is not random, it is special, and we might not stay here forever. Imagine compressing the space between stars to 1/10 of what surrounds Earth. That is the reality 10,000 light-years from the galactic center. Stars pack so tightly that the night sky on a planet orbiting one of those stars would blaze with thousands of points of light bright enough to read by. Beautiful, perhaps, but deadly. Close stellar encounters become inevitable at these densities. Every few million years, another star passes within a light year of your solar system. Sometimes closer, these encounters do not typically result in direct collisions between stars themselves, but the gravitational disruption to planetary systems can be catastrophic. Outer planets get stripped away, flung into interstellar space, or captured by the passing star. Comets in the outer reaches of the system get stirred up, some sent careening toward the inner planets, where they impact rocky worlds and sterilize surfaces with kinetic energy and heat. James Webb observed several star systems near the galactic center and found exactly this chaos. Planets in highly eccentric orbits, suggesting recent gravitational perturbations, debris disks around stars showing signs of disruption, systems lacking the stable architecture needed for long-term habitability. The data confirmed what models predicted. Planetary systems closer to the galactic core struggle to maintain the stability required for complex life to evolve. Radiation poses an even greater threat than stellar encounters. The galactic center region experiences supernova explosions at a rate roughly 100 times higher than our neighborhood. Some estimates suggest a supernova explodes within a few thousand light-years of the galactic center every few decades. Each explosion floods surrounding space with gamma rays, X-rays, and cosmic rays. Any planet within 1,000 light-years faces potential mass extinction. Any planet within a few hundred light-years gets sterilized completely, its atmosphere stripped away by radiation pressure. The combined effect creates an uninhabitable desert around the galactic core, not literally empty, but empty of the conditions needed for life as we understand it. Planets exist there. They orbit stars. Some might even have atmospheres. But they cannot host complex ecosystems over the billions of years required for intelligence to evolve. The environment resets too frequently. Radiation storms wipe out any progress life makes. Stellar encounters disrupt climates before biology can adapt. Webb also detected another problem in the inner regions: heavy element abundance. You might expect more heavy elements closer to the center because supernovae produce these elements, but the reality is more complicated. High supernova rates also mean high amounts of energetic feedback. Stellar winds and supernova shockwaves blow gas out of star-forming regions before it can collapse into new stars. This disrupts the recycling process that builds up heavy element concentrations. Some models suggest the inner galaxy might actually have lower metallicity than optimal for planet formation despite the higher supernova rate. There is also the question of the galactic bar. Stars within the bar follow chaotic orbits, looping back and forth along the bar's length. These orbits bring stars close to the central supermassive black hole periodically. Any planet in such a system would experience wild variations in gravitational environment, tidal heating, and radiation exposure as its parent star swung near the core and then retreated outward. Seasons on such a world would be defined not by axial tilt, but by proximity to galactic center. Deadly seasons measured in millions of years. Some researchers have proposed that the inner galaxy might host a different form of life, something adapted to high radiation and rapid environmental change. Perhaps microbes living deep underground on planets with thick crusts. Perhaps organisms with biochemistry that tolerates or even requires intense radiation. These are speculations, but they reflect an important reality. The galaxy is not uniformly hostile or uniformly habitable. It contains gradients, regions where different types of life might emerge based on local conditions. Earth's position far from these inner dangers is no accident. Complex life requires stability. It requires time measured in billions of years for evolution to progress from simple chemistry to consciousness. It requires protection from catastrophic events that would reset the biological clock repeatedly. The inner galaxy offers none of this. The outer regions where we reside provide exactly what life needs, but our safety is not permanent. The galaxy evolves, spiral arms shift, stars migrate inward and outward over cosmic time. In the far future, our descendants might find themselves in a galaxy where the habitable zone has moved and Earth sits in a region less friendly than today. 5 times more dark matter exists in the universe than normal matter. Everything you can see, every star, every planet, every gas cloud, every particle of dust, all of it combined, makes up less than 20% of the total mass. The rest hides in an invisible form that does not emit light, does not absorb light, does not interact with electromagnetic radiation at all. We know it exists only through its gravitational effects, and we swim through it constantly. The Milky Way sits embedded in a massive dark matter halo, extending hundreds of thousands of light years beyond the visible disk. This halo is not uniform. Dark matter clumps and streams through space in complex patterns shaped by billions of years of gravitational evolution. Some regions contain higher densities, other regions are relative voids. Our solar system moves through this invisible ocean as we orbit the galactic center, encountering different dark matter environments over time. James Webb cannot see dark matter directly. No telescope can. Dark matter does not glow. It does not reflect light. It passes through normal matter almost like a ghost, interacting only through gravity. But Webb can measure the effects of dark matter by observing how it bends light from distant galaxies through gravitational lensing. The telescope can track stellar velocities with incredible precision, revealing the gravitational pull from unseen mass. These indirect methods map where dark matter must concentrate. The data revealed something unexpected about our position. We sit in a region where dark matter density appears slightly lower than the galactic average at this distance from the center. Not a true void, but a relative underdensity. This matters because dark matter influences star formation, galaxy evolution, and potentially even the stability of planetary orbits over extremely long timescales. Lower dark matter density means weaker gravitational forces from the invisible mass. This might make our orbit slightly less bound to the galactic center, allowing greater variation in our path over billions of years. It might also affect how passing dark matter clumps interact with the solar system. Some theories propose that dense dark matter streams could occasionally pass through the solar system, their gravity perturbing comet orbits in the Oort cloud. If we live in a relative dark matter underdensity, these perturbations might happen less frequently than in other galactic regions. Webb also detected what astronomers call dark matter subhalos, smaller concentrations of dark matter embedded within the larger galactic halo. These subhalos are thought to be remnants of smaller galaxies that merged with the Milky Way billions of years ago. The normal matter from these galaxies got absorbed into the Milky Way's disk and bulge, but the dark matter remained in distinct clumps, moving through the galaxy on their original orbital paths. Several of these subhalos pass through our neighborhood, not close enough to pose immediate danger, but close enough that their gravitational influence might have affected the solar system's history. Some researchers have proposed that dark matter subhalo encounters could trigger comet showers by disturbing the Oort cloud. Others suggest these encounters might contribute to the solar system's gradual migration outward from the galactic center over billions of years. The exact nature of dark matter remains one of physics' greatest mysteries. Is it a new type of particle that interacts only through gravity? Is it made of multiple different components? Could it interact with normal matter through forces we have not detected yet? Webb's observations constrain these possibilities by mapping how dark matter distributes throughout the galaxy. If dark matter clumps too strongly, the distribution would look different. If it remains too smooth, the observed structure could not form. Our position within the dark matter halo also affects how we search for dark matter particles directly. Earth-based detectors sit deep within the halo, constantly passing through dark matter as we orbit. The local dark matter density determines how often these particles, whatever they are, might pass through the detectors. Webb's measurements of the halo density near Earth help physicists predict detection rates and interpret experimental results. There is also a darker possibility that some researchers explore cautiously. What if dark matter affects biological systems? Most evidence suggests dark matter passes through normal matter without interacting significantly. But if even rare interactions occur, and if those interactions happen frequently enough over evolutionary timescales, they might influence mutation rates or cellular chemistry. Living in a region of lower dark matter density might provide a slight biological advantage, reducing exposure to whatever subtle effects dark matter might have. This remains pure speculation. We have no evidence that dark matter affects life, but our ignorance about dark matter's true nature leaves room for possibilities we cannot rule out yet. We live surrounded by an invisible ocean we barely understand. Its presence shapes the galaxy. It might shape us. And as we continue our orbit, we drift through different currents in this dark ocean, heading toward regions where the density changes and the invisible becomes slightly more present. Rivers of stars flow through the Milky Way, not metaphorical rivers, actual streams of stars, remnants of smaller galaxies and star clusters that the Milky Way devoured billions of years ago. These stellar streams stretch across thousands of light years, winding through the galactic disk like cosmic ribbons, and several of them pass directly through our neighborhood right now. When a small galaxy approaches the Milky Way, tidal forces rip it apart. Gravity pulls harder on the near side than the far side, stretching the smaller galaxy into an elongated shape. Over millions of years, this stretching tears the galaxy to pieces. Its stars scatter into long streams that continue orbiting the Milky Way's center, following the path their parent galaxy once traveled. Eventually, these stars mix into the galactic population completely, but for hundreds of millions of years, they remain visible as coherent structures. James Webb identified at least 3 major stellar streams within 10,000 light-years of our position. The nearest passes within 2,000 light-years of the solar system. These streams contain old stars, some older than our own, moving at velocities different from the local stellar population. They cut through our region of space at odd angles, their orbits tilted relative to the galactic disk. One stream caught astronomers' attention immediately, named the Helmy Stream after the researcher who first identified it. This structure contains stars moving retrograde. They orbit backward compared to most stars in the galaxy. This retrograde motion proves they originated from a separate galaxy that collided with the Milky Way roughly 5 to 8 billion years ago. The parent galaxy got shredded, but its stars continue their backward journey, a ghostly reminder of ancient violence. The Helmy Stream passes through our region every few 100 million years as it completes its own orbit around the galactic center. We might be near one of these crossings now. Webb's velocity measurements of stars in the stream showed some moving toward our position, not on collision courses with the solar system, but close enough that their gravity could influence comets in the Oort cloud or perturb the orbits of distant objects in our outer solar system. Another stream, recently discovered and not yet officially named, appears to originate from a disrupted globular cluster. Globular clusters are ancient, dense balls of stars that orbit the galaxy outside the main disk. Sometimes, these clusters pass too close to the galactic center or experience a close encounter with a massive molecular cloud. Tidal forces tear them apart, scattering their stars into streams. This particular stream contains stars with unusual chemical compositions, different from typical Milky Way stars, confirming their distinct origin. Webb tracked individual stars within these streams, measuring their positions and velocities with extreme precision. This data revealed something troubling. Some stream stars have highly elliptical orbits that bring them much closer to the solar system periodically. These close approaches happen on timescales of tens of millions of years. The last close approach by a Helmy stream star might have occurred roughly 30 million years ago. The next could happen 30 million years from now. What happens when a star passes within a light year or two of the solar system? The gravitational perturbation is subtle but measurable. Objects in the Oort cloud, trillions of comets orbiting in the solar system's outermost reaches, get nudged onto new paths. Some fall inward, becoming long-period comets that swing past Earth and the other planets. Increased comet activity means higher chances of impacts. Some mass extinction events on Earth might correlate with these stellar flybys. The presence of stellar streams also complicates our understanding of the local stellar neighborhood. Astronomers once thought most nearby stars formed from the same general population, with similar ages and chemical compositions. Webb's observations showed greater diversity. Some nearby stars belong to streams. They are not native to this region. They are passing through, temporary visitors on journeys that will eventually carry them far from our neighborhood. This realization changes how we interpret the night sky. Those points of light overhead are not all locals. Some are travelers from destroyed galaxies. Some carry histories spanning billions of years and journeys across the entire galaxy. We share space with refugees from cosmic catastrophes, stars whose original homes no longer exist, and we are all moving together through the galaxy, stream stars and native stars alike, heading toward futures we cannot predict, but that web helps us see more clearly with every observation. The Milky Way is not perfectly flat. From the side, the galactic disk looks more like a warped record than a clean circle. The outer edges bend upward in some directions, downward in others. Ripples and waves distort the plane, and Earth does not sit exactly in the middle of this disk. We float slightly above the central plane by about 75 light-years. This vertical displacement might seem trivial compared to our horizontal distance of 29,000 light-years from the center, but it matters significantly for our local environment. The galactic plane is where most of the action happens. Star formation concentrates there. Molecular clouds gather in the densest regions. Dust accumulates in thick lanes running along the disk's midline. By sitting slightly above this activity, Earth enjoys a clearer view of the universe and reduced exposure to some dangers that plague systems embedded deep in the plane. James Webb measured our vertical position through careful observations of star distributions above and below our location. By counting stars at different heights and analyzing their distances, astronomers mapped the disk's thickness and determined where the solar system sits within that vertical structure. The infrared observations cut through dust that obscured previous attempts at this measurement, providing the most accurate vertical coordinate we have ever had. 75 light-years above the plane means we live in what astronomers call the thin disk. The Milky Way actually consists of multiple overlapping disk components. The thin disk contains most young stars and active star formation. It measures roughly 1,000 light-years thick. The thick disk, containing older stars, extends several thousand light-years above and below the plane. Then there is the stellar halo, ancient stars scattered far above and below in a roughly spherical distribution. Our position in the thin disk, but near its upper boundary, gives Earth a unique perspective. We look down on some star-forming regions. We see molecular clouds from the side rather than embedded within them. This vantage point might have helped life on Earth by reducing exposure to radiation from nearby star formation, which concentrates closer to the exact midplane where gas densities peak. But our vertical position is not static. The solar system bobs up and down through the galactic plane as we orbit, oscillating like a cork in water. This vertical oscillation takes approximately 70 million years to complete one full cycle. We move upward, reach a maximum height of roughly 250 light-years above the plane, then fall back down, cross through the plane, continue downward to roughly 250 light-years below, then rise again. Currently, we sit near the midpoint of this oscillation, moving upward. James Webb tracked this motion by measuring the vertical velocities of stars in our neighborhood. These measurements revealed that we are climbing toward the next maximum height at a rate of about 7 miles per second perpendicular to the galactic plane. In roughly 30 million years, we will reach the peak and begin descending. In 65 million years, we will cross the plane again, heading downward into the lower regions of the disk. This oscillation has consequences. Every time we cross through the galactic plane, we pass through the densest regions where molecular clouds concentrate. Some researchers propose that these plane crossings might correlate with increased comet impacts on Earth. Gravitational interactions with dense clouds could perturb the Oort cloud, sending comets toward the inner solar system. The timing is suggestive. We crossed the plane roughly 3 million years ago, and Earth has experienced a slight uptick in impact cratering since then. The vertical position also affects our exposure to cosmic rays. Cosmic rays propagate through the galaxy, but their distribution is not uniform. Higher densities exist near the galactic plane, where supernovae explode more frequently. By sitting above the plane, even by a relatively small 75 light-years, we reduce our cosmic ray exposure measurably. Over billions of years, this reduction might have provided an evolutionary advantage for life on Earth. Webb also discovered that our vertical position places us near a boundary between different populations of stars. Below us, younger stars dominate. Above us, older stars become more common. We exist at a transitional height where star formation still occurs but at reduced rates compared to the exact midplane. This environment might be optimal for hosting stable planetary systems, active enough to provide heavy elements and energy sources, but calm enough to avoid constant disruption from stellar chaos. The mapping of our vertical coordinate completes our three-dimensional address in the galaxy. We know our distance from the center, we know our position within the Orion arm, and now we know our height above the galactic plane with unprecedented accuracy. These three numbers define where we exist in space, and each one influences the conditions that made life on Earth possible. Our path through the galaxy is not smooth. We do not glide along a perfect circular track like a marble rolling around the inside of a bowl. Instead, we wobble, we oscillate. We drift in and out, up and down, tracing a complex three-dimensional spiral through space that changes shape over time. These wobbles come from gravitational interactions with every massive structure in the galaxy. The spiral arms pull on us as we pass near them. The galactic bar tugs from the center. Dark matter clumps exert invisible forces. Passing stars nudge our trajectory minutely. Molecular clouds we drift through create drag, slowing us slightly in some directions while their gravity accelerates us in others. All these influences combine into a constantly shifting motion that makes predicting our exact position millions of years in the future surprisingly difficult. James Webb measured these wobbles by tracking the three-dimensional positions and velocities of thousands of stars in our neighborhood over several years. Even small changes in stellar positions, measured across Webb's multi-year observation baseline, reveal the local gravitational environment. By comparing how different stars move, astronomers mapped the gravitational field we are all experiencing and determined how it perturbs our orbits. The most significant wobble happens perpendicular to the galactic plane. This vertical oscillation, roughly 70 million years per cycle, dominates our motion in that direction. But horizontal wobbles exist too. Our distance from the galactic center varies by approximately 3,000 light-years over the course of one complete orbit. We do not maintain a constant radius. We drift inward, then outward, following an elliptical path rather than a circle. Right now, according to Webb's measurements, we appear to be near the outer edge of this radial oscillation. Our distance from the galactic center is close to maximum. Over the next 100 million years, we will gradually drift inward, approaching the galactic center by roughly 1,500 light-years before swinging outward again. This inward drift will bring us closer to higher stellar densities, more active star formation regions, and increased radiation from the inner galaxy. Another wobble affects our speed around the galaxy. Our orbital velocity is not constant. It varies by several thousand miles per hour, depending on where we are in our orbit and what gravitational forces we are encountering. When we pass through a spiral arm density wave, the increased gravity accelerates us. When we move between arms, we slow down slightly. These speed variations create additional complications in calculating orbital timescales precisely. Webb also detected a wobble in our orbital plane itself. The galactic disk is warped, and as we move through this warp, the orientation of our orbit relative to the galactic center changes. Imagine a coin spinning on a table. Now imagine the table surface is not flat but wavy. The coin's spin axis would precess, wobbling as it followed the table's contours. Our orbit does something similar, precessing slowly as we navigate the warped structure of the galactic disk. These combined wobbles mean the solar system's path through the galaxy is chaotic in the technical sense. Not wildly unpredictable, but sensitive to initial conditions in ways that make long-term forecasts uncertain. We can calculate where we will be in 10 million years with reasonable confidence. Calculating our position in 1 billion years becomes much harder. Small errors in measuring current velocities and gravitational fields compound over time, spreading into larger uncertainties about future trajectories. The wobbles also affect our exposure to different galactic environments. A solar system on a perfectly circular orbit at constant height above the plane would experience relatively stable conditions. Our wobbling orbit carries us through varying stellar densities, different radiation environments, and encounters with diverse populations of stars and interstellar matter. This variability might have influenced Earth's biological history. Periods when our orbit brought us through denser regions could correlate with increased extinction rates. Periods in calmer neighborhoods might have allowed evolutionary radiations. James Webb continues monitoring these motions, refining our understanding of how the solar system moves through its cosmic environment. Each new observation adds precision to our trajectory calculations. Each data point helps predict what we will encounter next as we continue our wobbling journey around the galaxy. And some of what we will encounter looks more dangerous than anyone expected. Scattered around our position in the galaxy, ancient star clusters float through space like cosmic fossils. These globular clusters, dense spheres containing hundreds of thousands of stars, formed when the Milky Way was young. Most are 10 to 13 billion years old, nearly as old as the universe itself. They orbit the galactic center on paths that carry them through the disk periodically, and several will pass near our solar system within the next 100 million years. James Webb observed dozens of globular clusters in our region of the galaxy, measuring their distances, velocities, and chemical compositions with unprecedented accuracy. These observations revealed something remarkable. Some clusters follow orbits that intersect our path repeatedly over cosmic timescales. They are like cosmic markers, showing where the solar system has been and where it is going. One cluster, designated NGC 6397, approaches our neighborhood every 250 million years. It last passed within several thousand light years roughly 20 million years ago. The next close approach will occur in about 230 million years. Each time this cluster swings through our region, its gravity perturbs nearby stars and interstellar matter. The effects are subtle for individual objects, but significant when integrated over billions of years. These clusters serve as tracers of galactic structure and evolution. Because they are so old and their orbits are so well defined by gravity, astronomers can work backward to determine where they originated and how the galaxy has changed since their formation. Webb's precise measurements of cluster positions and velocities provided new constraints on the Milky Way's merger history. The data showed that several clusters likely formed in smaller galaxies that merged with the Milky Way billions of years ago. The chemical composition of stars in these clusters also tells a story about our galactic environment's evolution. Early in the universe, only hydrogen and helium existed. Heavier elements formed inside stars and spread through space when those stars exploded as supernovae. Globular cluster stars formed early, so they contain lower abundances of heavy elements compared to younger stars. By measuring exactly how much iron, carbon, and other elements these ancient stars contain, astronomers trace the chemical enrichment history of the galaxy. Webb found that clusters passing through our neighborhood show a range of chemical compositions. Some are extremely metal-poor, formed when the galaxy had produced very few heavy elements. Others contain slightly more metals, indicating formation during a later phase of galactic evolution. This diversity suggests our region of the galaxy received contributions from multiple populations of stars over billions of years. We live in a chemically enriched environment built up gradually by generations of stellar death and rebirth. The orbits of these clusters also provide information about the dark matter distribution in the galaxy. Dark matter's gravity shapes how clusters move. By tracking cluster positions over time and comparing their actual motions to predictions based only on visible matter, astronomers infer how much dark matter must exist and where it concentrates. Webb's multi-year observations captured small changes in cluster positions, refining dark matter maps around our location. Some clusters show signs of tidal disruption. As they pass through the galactic disk, especially through dense molecular clouds, tidal forces pull stars away from the cluster's outer edges. These escaped stars form streams, similar to the stellar streams from disrupted galaxies but on smaller scales. Webb detected several such streams associated with clusters in our neighborhood. These streams contain some of the oldest stars in the galaxy, now drifting freely through space after being liberated from their birth clusters billions of years ago. The presence of ancient globular clusters near our position raises questions about their influence on the solar system's history. Did any cluster pass close enough to perturb the Oort cloud significantly? Could encounters with clusters have sent comets toward Earth during critical periods of biological evolution? The distances involved are usually too large for direct gravitational effects, but even distant encounters leave subtle traces. Webb continues monitoring these ancient sentinels, mapping their journeys through the galaxy with increasing precision. Each cluster represents a different chapter in the Milky Way's history. Each orbit, intersecting ours, connects our solar system to events that happened billions of years before Earth formed. We share the galaxy with these ancient survivors, following paths that occasionally converge in the cosmic dance. Spiral arms do not stay in their lanes. They collide. They overlap. They create zones where density waves from different arms intersect, compressing gas to extreme densities and triggering violent bursts of star formation. James Webb mapped several of these collision zones within 20,000 light-years of our position, and what the telescope found suggests our neighborhood is more active and more dangerous than anyone realized. The Orion arm and the Perseus arm interact along their boundaries. These two structures do not simply sit side by side. Their spiral patterns bring them close enough in some regions that their gravitational influences merge. Gas flows from one arm into the other. Stars born in one structure drift into the other over millions of years. The boundary between them is not a clean line, but a turbulent mixing zone where conditions shift dramatically across relatively short distances. Webb identified one particularly active collision zone, roughly 8,000 light-years from our current position, in the direction of the constellation Cygnus. Here, the Orion and Perseus structures appear to overlap directly. Gas compressed in this region has spawned dozens of massive star-forming complexes, each containing enough material to create thousands of stars. The infrared observations revealed protostars still wrapped in their birth cocoons, massive stars already burning through their fuel at prodigious rates, and supernova remnants from stars that lived fast and died young. This collision zone moves. The spiral arms rotate at different speeds, and the intersection point shifts position over millions of years. Currently, this zone is moving away from our location, but it will not always do so. The dynamics of spiral arm rotation will eventually bring another collision zone closer to us. In roughly 40 million years, a different intersection point between Orion and Sagittarius arms will pass within a few thousand light-years of the solar system. What happens in these collision zones matters for life. The intense star formation produces massive stars that flood surrounding space with ultraviolet radiation. These stars live only a few million years before exploding as supernovae. Multiple supernovae in a small region create superbubbles, vast cavities blown in the interstellar medium by overlapping shock waves. These bubbles can span hundreds of light years, sweeping up gas and dust, clearing out space, and creating shells of compressed material that trigger new rounds of star formation. Any planetary system caught in a superbubble faces serious risks. The radiation levels spike, cosmic ray bombardment increases, the stellar wind environment becomes chaotic. If Earth existed in such a region when life was beginning, sterilization would be likely. Even established biospheres might struggle to survive the onslaught. Our distance from current collision zones provides crucial protection. But Webb also discovered something unexpected about these zones. They produce organic molecules at rates far higher than quieter regions of the galaxy. The intense radiation and turbulent gas dynamics drive complex chemistry, molecules that serve as building blocks for life form in abundance. When these molecules get incorporated into new planetary systems forming in the collision zones, they deliver a head start for potential biology. This creates a paradox. Collision zones are too dangerous for complex life to survive long term, but they might be the best places for generating the chemical precursors life needs. Planetary systems that form in collision zones but then drift away into quieter regions could have advantages. They receive an initial boost of organic chemistry, then migrate to calmer environments where biology can flourish without constant disruption. The solar system's history might include passage through such zones. We formed roughly 4.5 billion years ago, somewhere in the Orion arm. Where exactly remains uncertain, but computer simulations suggest we might have originated in a more active region than we occupy now. If true, Earth's early chemistry might have benefited from collision zone processes before we drifted to our current safer location. Webb continues mapping collision zones throughout the nearby galaxy, tracking their evolution and movement. These observations help predict which regions will become more active in the future and which will calm down. For planetary scientists searching for habitable worlds, this information is crucial. Avoid systems in collision zones now. Consider systems that recently left collision zones. Think about galactic dynamics when assessing where life might emerge and thrive. Our neighborhood appears calm now, but the galaxy is dynamic. Collision zones will approach. We will pass through more turbulent regions. Understanding where these zones exist and how they move helps prepare for what comes next on our galactic journey. Between the spiral arms, vast regions contain almost nothing. No bright stars, no active star formation, no dense molecular clouds. Just old, faint stars drifting through space at low densities, separated by distances that dwarf even the already immense gaps between stars in our current neighborhood. These voids stretch thousands of light years across, and our orbit is carrying us toward one. James Webb mapped these void regions by searching for the absence of light. Where optical telescopes see darkness, astronomers assume either dust is blocking the view or nothing exists there. Webb's infrared vision penetrates dust, so when the telescope sees nothing, that absence is real, true voids. Regions where star formation stopped billions of years ago and the existing stellar population has thinned out through natural stellar death. The void between the Orion and Sagittarius arms extends roughly 6,000 light-years across. Not completely empty, but containing stellar density only 10% of what we experience in our current position. In 80 million years, our orbit will carry us deep into this void. The night sky on Earth will look dramatically different. Fewer bright stars will be visible. The Milky Way's band will appear dimmer from our perspective inside it. the solar system will float in a much lonelier region of space. Why do these voids exist? Spiral arms are density waves, regions where stars and gas crowd together temporarily as they orbit. Between the waves, density drops. Star formation requires dense gas, so regions between arms produce few new stars. Over time, the massive stars that do form between arms die off quickly. Their lifetimes measured in millions of years mean they never survive to the next spiral arm passage. Only lower mass, dimmer stars persist, and these are harder to detect and more spread out. Webb also found that void regions are not uniform. Some sections contain slightly higher densities than others. Some areas have more dust and gas, suggesting star formation might still happen occasionally. Other sections appear completely depleted, scrubbed clean by past supernova explosions or stellar winds that blew material out of the region entirely. The void we are approaching contains multiple subregions with different characteristics. Entering a void has consequences. Stellar encounters will become even rarer than they are now. This reduces gravitational perturbations to the Oort cloud, potentially decreasing comet impacts on Earth. Radiation from nearby stars will drop because there will be fewer nearby stars. The local interstellar medium will thin out, reducing the drag force on the solar system's motion through space. In some ways, the void offers a safer environment than our current position. But voids also present challenges. The reduced stellar density means fewer opportunities for observing other planetary systems. The search for habitable worlds and potential biosignatures becomes harder when target stars spread farther apart. The interstellar medium, while thinner, might have different composition. Void regions contain older gas that has been processed through fewer stellar generations, meaning lower abundances of heavy elements in the diffuse material between stars. Webb detected something troubling about the void's edges. Where the Orion arm transitions into the void, the stellar density drops sharply over a relatively short distance. This creates a gradient, a boundary region where conditions change rapidly. Our solar system will cross this boundary in roughly 70 million years. The transition might take only a few million years of galactic time, essentially instantaneous compared to our orbital period. What happens during this transition? The local radiation environment shifts. The gravitational influence from nearby stellar populations changes. The density of cosmic rays might vary as we move from a region with active supernovae to one where such events are rare. These rapid changes could affect Earth's climate, its magnetic field interactions with the solar wind, and potentially even the rate of comet delivery from the Oort cloud. Some researchers propose that void passages might correlate with certain patterns in Earth's geological and biological record. The evidence remains controversial, but the timing is suggestive. Our solar system appears to pass through voids on a schedule that might match up with some long-term climate cycles and extinction patterns. More data is needed to confirm or refute these correlations. The void also represents an opportunity. In these quieter regions, astronomers can study the galactic background environment more clearly. Radiation from distant galaxies becomes easier to detect when local star formation does not create as much interfering signal. The cosmic microwave background, the afterglow of the Big Bang, shows up more clearly against a darker local sky. Some of the most important cosmological observations might become possible only when we enter the void. Our trajectory toward this empty region is certain. The galactic mechanics are inexorable. We will spend perhaps 50 million years crossing through the void before emerging into the Sagittarius arm on the other side. During that time, Earth will experience conditions unlike anything in recent geological history. A lonelier galaxy, a darker sky, a different cosmic environment, and we cannot predict everything that environment will bring. For decades, astronomers searched for Earth-like planets around nearby stars without fully understanding our galactic context. They picked targets based on stellar properties, distance from Earth, spectral type, age, metallicity, all important factors, but they overlooked something crucial. Where those stars exist in the galaxy matters just as much as their individual characteristics. The revised measurements of our galactic position changed everything about this search. If we sit farther from the galactic center than previously thought, and if the Orion arm is a major structure rather than a minor spur, then the stars we share this region with are not random samples of the galactic population. They represent a specific environment, a specific set of formation conditions, a specific exposure history to radiation, stellar encounters, and chemical enrichment. James Webb's observations allowed astronomers to map the three-dimensional distribution of nearby stars with unprecedented accuracy. This mapping revealed structure in what appeared to be a random scatter. Stars in our neighborhood organize into loose groups, remnants of ancient star-forming events. Some stars formed together billions of years ago and still drift through space as companions, even though they are no longer gravitationally bound. Other stars are recent additions, having drifted into our region from other parts of the Orion arm. This structure matters for the exoplanet search. Stars that formed together likely have similar chemical compositions. They built their planets from similar raw materials. If one star in a group hosts a habitable world, others in the same group might too. Identifying these family relationships helps target searches more efficiently. Webb also measured the ages of nearby stars more accurately by observing their infrared spectra. Different elements in a star's atmosphere absorb light at specific wavelengths. The exact pattern of absorption depends on the star's age, temperature, and composition. By analyzing thousands of stellar spectra, astronomers built a detailed census of our stellar neighborhood. The results surprised everyone. Most nearby stars are older than our own. The local stellar population skews toward ages of 6 to 8 billion years. This means their planets, if they have planets, have had more time for life to evolve than Earth has. Any civilization that emerged on worlds orbiting these older stars could be billions of years ahead of us technologically. This realization shifted the focus of searches for intelligent signals. Look at older stars first. They have the biggest head start. But age alone does not guarantee habitability. Webb discovered that many older stars in our neighborhood have higher metallicities than expected. They contain more heavy elements than typical for their age. This suggests they formed in a region that experienced rapid chemical enrichment, possibly from multiple nearby supernovae in quick succession. Planets around these stars might have unusual compositions, more iron, more silicon, different ratios of elements than Earth has. Whether such planets could support life remains an open question. The new understanding of our position also revealed that we live in a relatively stable region. Compared to stars deeper in the Orion arm or closer to spiral arm intersection zones, our neighborhood experiences lower rates of stellar encounters, lower supernova rates, and calmer interstellar conditions. This stability might be rare. Most regions of the galaxy that support star formation are more chaotic. We might occupy a sweet spot, a local minimum in galactic turbulence. If true, then Earth-like planets might concentrate in regions similar to ours, not uniformly distributed throughout the galactic habitable zone, but clustered in pockets where conditions stay stable long enough for complex life to evolve. Webb's mapping of our galactic environment helps identify where these other pockets might exist. Look for regions between major spiral arms. Look for positions at similar distances from the galactic center. Look for areas with moderate star formation rates and older stellar populations. The telescope also identified something concerning. Several nearby stars will pass much closer to the solar system than previous calculations predicted. These close approaches happen because the stars follow slightly different orbits than we do. Over millions of years, the distance between us decreases. Webb's precise velocity measurements revealed that at least 3 stars will pass within 2 light-years of Earth in the next 5 million years. These encounters could affect the search for life on exoplanets around those stars. If we eventually develop the capability to send probes to other star systems, close approach stars become prime targets. The reduced travel distance makes missions feasible that would otherwise require technology far beyond our current capabilities. Our shifting galactic position creates opportunities that did not exist before. The exoplanet search is now a galactic science. It is not just about finding planets. It is about understanding where in the galaxy conditions favor planet formation, chemical evolution, and biological development. Webb's mapping of our true position provides the context needed to interpret exoplanet discoveries meaningfully. Each new world is not just a point of data. It is a sample of a specific galactic environment, a test of how location shapes outcomes. And as our understanding of our location improves, the search for life becomes more focused, more strategic, and more likely to succeed. The galaxy is not uniformly bathed in radiation. Intensity varies dramatically depending on where you sit, creating zones of safety and zones of danger. These zones are not static. They shift as spiral arms rotate, as supernovae explode, as stellar populations age and die. James Webb mapped the radiation environment throughout our region of the galaxy, and the results revealed that Earth exists in a narrow corridor of relatively low exposure, surrounded by regions where radiation levels would sterilize unprotected life. Cosmic rays form the background radiation field throughout the galaxy. These high-energy particles, mostly protons accelerated to near light speed by supernova shockwaves, zip through space constantly. They penetrate planetary atmospheres. They interact with magnetic fields. They create showers of secondary particles when they strike atoms. Life on Earth's surface avoids most of this damage because our atmosphere is thick and our magnetic field strong, but cosmic rays still contribute to mutation rates and cancer risks. Webb measured cosmic ray intensities indirectly by observing their effects on the interstellar medium. When cosmic rays strike hydrogen atoms in space, they create specific emission signatures that infrared instruments can detect. By mapping these signatures across thousands of light years, astronomers built a three-dimensional picture of cosmic ray density. The map showed clear structure, higher densities near active star-forming regions, lower densities in voids, and a moderate, relatively stable density in our current neighborhood. At our distance from the galactic center, cosmic ray flux measures approximately 1 particle per square centimeter per second. This might sound high, but it is actually low compared to regions 5,000 light-years closer to the core, where the flux triples. It is also low compared to regions inside active spiral arms, where supernova rates drive the flux even higher. We exist in a cosmic ray minimum, a radiation shadow that makes complex life more viable. But this shadow is not permanent. As we orbit the galaxy and pass through different environments, cosmic ray exposure varies. Computer models based on Webb's data predict that cosmic ray flux will increase by roughly 50% when we enter the Sagittarius arm in 80 million years. It will spike even higher during our next passage through the Perseus arm. These increases might stress Earth's biosphere, though probably not enough to cause total extinction unless multiple unlucky events coincide. Gamma rays present a different threat. These ultra-high energy photons come primarily from supernova explosions and gamma-ray bursts. Unlike cosmic rays, which spread diffusely through the galaxy over millions of years, gamma rays travel in directed beams that deposit their energy in concentrated bursts. A gamma-ray burst aimed at Earth from a few thousand light-years away could strip the ozone layer in hours, exposing the surface to lethal ultraviolet radiation from the sun. Webb searched for potential gamma-ray burst progenitors in our neighborhood. These are massive star systems, nearing the end of their lives, rotating rapidly, and positioned such that their eventual explosion might direct gamma rays toward us. The telescope identified several candidates within 10,000 light-years, not immediate threats, since these stars might survive another million years or more, but worth monitoring. The closest candidate sits roughly 8,000 light-years away, close enough to cause significant damage if its rotation axis points our direction when it explodes. The galactic center contributes its own radiation hazard. X-rays and gamma rays stream outward from the supermassive black hole and the dense star cluster surrounding it. At our revised distance of 29,000 light-years, this radiation has weakened considerably compared to inner regions, but it still contributes to the background. During periods when the black hole actively accretes material, X-ray fluxes increase across the entire galaxy. We cannot escape this completely, but distance helps. Webb also detected radiation from exotic sources. Pulsars, rapidly spinning neutron stars, emit beams of radiation that sweep across space like cosmic lighthouses. Several pulsars in our region point their beams in our general direction. The radiation doses are small, but measurable. Over millions of years, even small doses accumulate. Some researchers speculate that pulsar radiation might have influenced Earth's atmospheric chemistry during certain geological periods. The magnetic environment matters too. The galaxy has a large-scale magnetic field, twisted and compressed by the rotation of the disk and the motion of ionized gas. This field deflects cosmic rays, channeling them along magnetic field lines and creating corridors of higher and lower radiation. Webb cannot detect magnetic fields directly, but by observing polarized light from dust grains that align with the field, astronomers map its structure. The results showed that we currently move through a region where the magnetic field provides moderate shielding, reducing cosmic ray exposure below what we would experience in a field-free zone. Our position is fortunate. Not perfectly safe, but safer than most regions of the galaxy at comparable distances from the center. This luck might be temporary, a consequence of where we happen to be in our orbit at this moment in galactic history. Or it might reflect something deeper about how planetary systems that host life end up in preferred locations through selection effects we do not fully understand yet. Either way, the radiation map matters for the future. Knowing what we will face as we continue our orbit helps predict challenges Earth's biosphere must survive. At the exact center of the Milky Way, a monster lurks. Not metaphorical, a real gravitational beast with a mass equal to 4 million suns compressed into a region smaller than our solar system. This supermassive black hole, called Sagittarius A*, anchors the entire galaxy. Every star, every planet, every atom of gas orbits around it, held in place by gravity that warps space itself. 29,000 light-years separate us from this object. That distance sounds safe, comforting even, but gravity extends infinitely. It weakens with distance, following the inverse square law, but it never vanishes completely. Right now, at this moment, Sagittarius A times pulls on Earth with measurable force, tiny compared to our star's gravity or even the moon's tidal influence, but real and constant. We orbit because of that pull. James Webb cannot observe the black hole directly. Black holes emit no light. They are literally black, but Webb can see the effects. Stars near the galactic center orbit Sagittarius A times at incredible speeds, some moving at over 5,000 miles per second. These stellar orbits trace the black hole's gravitational field with precision. By measuring how these stars move, astronomers calculate the black hole's mass and position exactly. The new measurements confirmed something unsettling. Sagittarius A times is more massive than earlier estimates suggested. Not dramatically more, but enough to matter. The updated mass estimate is 4.3 million solar masses, compared to 4.1 million from previous observations. That extra mass increases its gravitational pull on everything in the galaxy, including us. This stronger gravity affects our orbital calculations. A more massive central black hole means slightly faster orbital velocities at every distance. It means our orbit takes slightly less time to complete. It means the gravitational forces holding the galaxy together are stronger than we thought. which has implications for dark matter distribution and galactic structure models. Small corrections, but they propagate through every calculation about galactic dynamics. The black hole also influences the galaxy through more than just its steady gravitational pull. Sagittarius A times occasionally feeds. Gas and stars that drift too close get torn apart by tidal forces. As this material spirals inward, gravitational compression heats it to millions of degrees. The superheated matter radiates energy across the spectrum before crossing the event horizon and disappearing forever. These feeding events create bursts of X-rays and gamma rays that wash across the entire galaxy. Webb detected evidence of a major feeding event that occurred roughly 200 years ago. The radiation from this event has been traveling outward through space ever since. It reached Earth recently, and astronomers observed it as a faint glow in the infrared from molecular clouds near the galactic center that absorbed and re-emitted the energy. This echo of ancient violence reveals that Sagittarius A times was much more active in the recent past than its current quiet state suggests. If the black hole experiences major feeding episodes every few hundred years, then over millions of years, Earth has been bathed in thousands of radiation pulses from the galactic center. Each pulse adds to the cumulative radiation dose life on Earth must tolerate. The intensity at our distance is not immediately deadly, but over evolutionary timescales, these events might contribute to mutation rates and influence biological evolution in ways we cannot yet measure. The black hole's gravity also affects the galactic bar. This elongated structure of stars rotates as a nearly rigid body, but its rotation rate depends on the central mass. A more massive black hole means the bar rotates differently than models predicted. This changes how the bar's gravity influences outer regions of the galaxy, including our neighborhood. The resonances shift. The timing of gravitational perturbations changes. Our orbital wobbles might be partially driven by these black hole-mediated effects. Webb also observed stars in highly eccentric orbits around Sagittarius A*. These stars swing close to the black hole, experience extreme gravitational acceleration, then swing back out into less extreme regions. Some of these stars pass through the galactic disk periodically. Their high velocities mean they can travel far from the center, potentially reaching our distance from the core. If one of these high-velocity stars ever passed through our neighborhood, its gravity could perturb the Oort cloud severely. The probability of such an encounter is low, but not zero. Computer simulations based on Webb's observations of the central stellar population suggest roughly one high-velocity star passes within 10,000 light-years of our position every 50 million years. Most of these encounters are distant enough to cause minimal disruption, but occasionally, within a few thousand light-years, the perturbation becomes significant. Our connection to the supermassive black hole at the galaxy's heart is not abstract. It is physical, gravitational, radiative. The black hole shapes our orbit. It influences our environment. It pulses radiation toward us periodically. We exist in its domain, subject to forces that originate from a singularity we will never approach but can never escape. And that gravitational tether will only grow stronger over time. 50 million years from now, Earth will not orbit where it does today, not even close. The solar system will have traveled 1/5 of the way around the galaxy, crossing roughly 12,000 light-years of space. We will occupy a completely different galactic environment, different neighbors, different radiation exposure, different skies. The change will be profound. James Webb's measurements of our current position and velocity, combined with detailed models of galactic structure, allow astronomers to predict our future location with reasonable accuracy. The calculations account for the gravitational pull from the galactic center, the influence of spiral arm density waves, perturbations from the galactic bar, and the effects of dark matter distribution. These models are not perfect, but they provide a glimpse of where we are headed. In 50 million years, we will be deeper into the transition between the Orion arm and the void beyond it. Stellar density in our neighborhood will have dropped to roughly half of current levels. The bright stars that currently dominate our night sky, many of them massive and short-lived, will have died. Some will have exploded as supernovae, others will have faded to white dwarfs. The constellations will be unrecognizable, not just because Earth's axial precession changes which stars we see, but because the stars themselves will have moved and many will no longer exist. Our distance from the galactic center will have increased slightly. The outward drift in our orbit will carry us perhaps 200 light-years farther from Sagittarius A*. This tiny change in the context of our 29,000 light-year distance will nonetheless reduce cosmic ray exposure measurably. Every bit of extra distance helps when radiation is concerned. We will also be descending through the galactic plane. Currently sitting about 75 light-years above the midline, we are moving upward toward a maximum height of roughly 250 light-years. But 50 million years from now, we will have reached that peak and begun falling back down. We will be perhaps 180 light-years above the plane, still climbing but approaching the turning point. The vertical position matters for dust exposure. The galactic plane concentrates dust and gas. By staying above it, we reduce the density of material the solar system plows through. Less dust means less drag on our orbit. It also means better visibility for observing the rest of the universe. Future astronomers will have clearer views of distant galaxies as we reach peak height above the plane. Webb's models predict we will encounter several stellar streams during this 50 million year journey. The Helmy stream will pass relatively close, perhaps within 3,000 light-years. Its gravity might perturb comets in the Oort cloud, sending some toward the inner solar system. Earth could experience an uptick in comet impacts during this period. Not catastrophic necessarily, but noticeable in the geological record if civilization or its descendants still track such things. The radiation environment will shift as we move farther from active star-forming regions. Supernova rates in our neighborhood will decline. Cosmic ray flux will drop. Ultraviolet radiation from massive stars will decrease. In many ways, the next 50 million years will be safer than the last 50 million. We are entering a calmer phase of our galactic orbit. But calm brings its own challenges. Fewer nearby stars means fewer opportunities for stellar encounters, which sounds like a good thing until you consider that stellar encounters sometimes provide beneficial perturbations. They can inject angular momentum into planetary systems, stabilizing orbits that might otherwise decay. They can deliver fresh material from the interstellar medium. They can trigger cloud collapse that leads to new star formation in the neighborhood. Too much calm might be almost as problematic as too much chaos. The sun itself will have changed by this point in the future. 50 million years is a noticeable fraction of a stellar lifetime for a star like ours. Core fusion will have progressed. The sun will be slightly brighter, perhaps 1% more luminous than today. This increased output will warm Earth's surface unless other factors compensate. Climate will shift. Oceans might evaporate faster. The habitable zone around our star will move outward, potentially making Mars more Earth-like while pushing Earth toward Venus-like conditions. These internal solar system changes will interact with our changing galactic environment in complex ways. More radiation from a brighter sun, but less radiation from the galactic neighborhood. Different cosmic ray bombardment affecting atmospheric chemistry. Different stellar wind interactions as we move through varying interstellar medium densities. The combined effects are difficult to predict precisely, but they will matter for any life that persists on Earth or spreads to other worlds in the solar system. The night sky will tell stories of this journey to anyone who looks up. Different constellations, different bright stars. The Milky Way's band across the sky will appear dimmer as we move between spiral arms. The Andromeda galaxy will loom larger, its collision with the Milky Way still hundreds of millions of years away, but creeping closer with each passing millennium. 50 million years is nothing to the galaxy, a blink, a moment between moments. But for Earth, for life, for whatever civilizations might exist by then, it represents fundamental change. A different cosmic address, a different set of challenges and opportunities, a different chapter in the solar system's long story. Every revelation about our galactic location rewrites the equation for finding life beyond Earth. For decades, scientists searched for habitable worlds using one basic assumption. Life could emerge anywhere in the galactic habitable zone where conditions were roughly similar to Earth. Distance from the galactic center mattered, star type mattered, planet size and orbit mattered. But the specific galactic neighborhood was treated as background detail. James Webb destroyed that assumption. Our location is not generic. The Orion arm is a major structure with specific properties. Our distance from the galactic center of 29,000 light-years places us in a narrow range where radiation exposure, stellar density, and chemical composition combine favorably. Our height above the galactic plane reduces dust and cosmic ray bombardment. Our position between major spiral arms provides stability. These factors do not just make Earth habitable, they make it possible for complex life to evolve over billions of years without catastrophic interruption. If our location is special, then life might concentrate in similar locations throughout the galaxy, not spread uniformly across the habitable zone, but clustered in pockets where conditions match ours. This changes the search strategy completely. Instead of surveying stars randomly, astronomers should target regions that mirror our galactic environment. Look for planetary systems in major spiral arms between activity peaks. Look for stars at similar distances from their galactic centers. Look for positions above the galactic plane where radiation drops. Webb began this targeted search by mapping nearby stars in 3 dimensions with unprecedented precision. The telescope identified which stars share our galactic environment most closely. These are the prime candidates for hosting Earth-like worlds with evolved biospheres. Some lie within a few dozen light-years, others spread across hundreds of light-years. Each represents a potential twin of Earth, not just in planetary properties but in cosmic context. The data revealed something profound. Stars that match our galactic environment characteristics cluster in specific regions. They are not randomly scattered. They concentrate in areas where spiral arm structures created similar formation conditions billions of years ago. This clustering suggests that if technological civilizations exist, they might appear in groups, islands of intelligence, separated by vast stretches of space where conditions never favored complex life. This has implications for detecting signals from other civilizations. If life clusters in specific galactic environments, then searches for radio transmissions or other technosignatures should focus on those regions. The empty voids between spiral arms become low-priority targets. The collision zones where spiral arms intersect might host abundant life, but probably not technological civilizations because the environment is too unstable for intelligence to develop. The sweet spots are regions like ours, between major activity centers, but still within active spiral arms. Webb also changed the timeline for how we think about life's emergence. The telescope's observations of nearby stellar populations revealed that most stars in our neighborhood are older than our Sun. Many are 2 to 3 billion years older. If planets around these stars developed life on similar timescales to Earth, then those biospheres could be billions of years more advanced. The implications stagger the imagination. Civilizations that old might have colonized entire regions of the galaxy. They might have technologies that look like magic or even like natural phenomena to us. The fact that we have not detected such civilizations presents a puzzle. If favorable galactic locations are rare and we occupy one, and if older stars in our neighborhood had similar advantages, then where is everyone? This silence might mean technological civilizations are rarer than optimists hope. Or it might mean they exist but remain quiet, either by choice or because communication across interstellar distances is harder than we assume. Or perhaps we are looking in the wrong ways, searching for radio signals when advanced civilizations use entirely different technologies. Webb's mapping of our location also affects predictions about life's distribution across cosmic time. The galactic habitable zone was different billions of years ago. Spiral arms occupied different positions. Stellar densities varied. Chemical compositions changed as generations of stars lived and died. Our current favorable location might have been less favorable in the past, and other regions that are dangerous now might have been safer then. Life could have emerged in many locations, but survived only in places that remained stable as the galaxy evolved. This temporal dimension adds another layer of complexity. Finding life is not just about identifying the right locations now. It is about recognizing that galactic environments change over billions of years, and only certain regions maintain habitability long enough for complex life to develop. Earth might be one of the lucky ones, a planetary system that formed in the right place at the right time and stayed in favorable conditions long enough for intelligence to emerge. The search for life beyond Earth is fundamentally a search for places that mirror our cosmic context. Webb gave us the tools to identify those places with unprecedented precision. The telescope mapped our galactic neighborhood. It revealed our true position. It showed us which nearby stars share our environmental history. The next step is to examine those stars for biosignatures, chemical signs of life in planetary atmospheres. Then we wait and listen, searching for signals that would prove we are not alone in our peculiar galactic niche. Because if life exists elsewhere, it probably exists in places like this, in major spiral arms, between the chaos of active star formation and the emptiness of voids. At specific distances from galactic centers, where radiation balances between too much and too little, in neighborhoods that have remained stable for billions of years, allowing evolution the time it needs to produce complexity. James Webb showed us where we are. Now we use that knowledge to find out if anyone else exists in similar cosmic circumstances. The search continues, more focused than ever before, guided by the revelation that location is not just background detail. Location is everything.